Thank you. Yep, my name is Milad Kazurunian. I'm going to be presenting the joint work with these good folks here on using type-level computations to type-check Ruby programs. So just to provide some very brief background, Ruby is a popular dynamic scripting language. It's dynamically typed, object-oriented, and reflective, and it's most commonly used for web development, most famously in the framework Ruby on Rails. And the ultimate motivation behind our work is to gain the benefits of adding static types to Ruby programs. So there are many well-known benefits. We can catch bugs early. It makes it easier to write correct and safe code, and it provides a useful documentation for the programmer. Now the starting point for our work is this existing tool called RDL, which is an existing system for adding static types to Ruby. So with RDL, we can optionally choose which portions of our program we want to type check, add annotations, and check just those portions. And RDL includes an expressive type language with nominal types, generic types, singletons, unions, and many more. So for a very simple example, we see a Ruby method foo here that just returns to us a string that says 42. And using RDL, we can attach this type annotation that says foo should return an integer, and we'd be able to catch the obvious discrepancy here. But there are places where RDL falls short, and one of those places is in type checking database queries. So an example of a simple query from a Rails program is shown here. In Rails, the most common way to query the database is using this embedded DSL called ActiveRecord. So what's going on in this query is user is a Ruby class that maps to a table of users in the database. Exists is an ActiveRecord method for checking if a particular record exists in that table. And the exist method takes this hash that maps username to the string Alice. So username is a Ruby symbol, which is just an intern string, and it names the column we want to look up in that table. And the string Alice is the value we want to look up in that column. So all this query is saying is, are there any users with the username Alice? And our question now is, how do we actually type check this query? And to be more precise, how do we check properties like username is actually a column belonging to the user table, and the string Alice has the correct type for the username column? So our first attempt could just be to use polymorphic types and say exist takes an input type that's a hash that maps symbols to any kind of object. And now using this, the example we just saw would type check, but the problem is the type is very imprecise, and it would also accept some incorrect kinds of queries. So for example, we could look up a non-existent column called fake column, or we could look up the username 42, even though username expects a string. Both of these queries are errors. Neither of them would be caught by this type. So our second attempt could be to try to overload the exist method. And for this purpose, RDL has what are called finite hash types. And these are just like a precise kind of hash type that tells us the names of keys and the types of values in a hash. So using these finite hash types, for every class that maps to a table in the database, we could write a separate type for exists that reflects the schema of that class. So for the user class, we could say exist takes an input hash that maps username to string and ID to integer. For another class email, we could say it maps email to string and ID to integer, and so on for every table class in our program. And this would solve the imprecision problem that we just saw, and we'd be able to catch those errors we saw on the previous slide. But unfortunately, it's not going to work for more intricate kinds of queries, and in particular, when the receiver of an exist call is more complex. Which brings us to type checking joins. So this example was taken and simplified from one of our benchmarks. And the first thing we do is join the user and the email tables. And after doing that, we call the exist method again, but this time when we call it, we're looking up both the staged and the username columns of the exist table and the email column of the email table. So that overloading exists approach we just saw isn't going to work in this case because we're looking up columns in multiple tables. And so the question now is really what type should joins return, and in particular, what type should it return such that we can check that the columns and the values in the exist query are correct. And the real trick here is that the return type for joins depends on both the receiver and the argument to the joins call. So one thing we could try is, again, overloading this time all possible joins combinations, but this is going to be infeasible for larger programs. So for one of our benchmarks, we found there were over 430,000 possible 2- and 3-way joins combinations. We couldn't feasibly generate all these types and use them to type check a program in a reasonable amount of time. Which brings us to our solution, which is to make use of type-level computations for Ruby library methods. So our contribution is to add type-level computations to RDL, or what we call CompTypes for short. And we came up with this different name because these really represent a limited form of dependent type. And the way these will work is we're going to allow Ruby expressions within a method's type signature, and when we actually evaluate those expressions, we'll get some precise input and output types we can use to precisely type check our program. And that's going to enable us to type check database queries, and by precise, I mean we can check things like the column belongs to the table we're looking up. And as we'll see, it's also going to reduce the need for manually inserted typecasts. So we wrote CompTypes for a number of Ruby libraries and used them to check 6 popular Ruby applications. And in the process, we found 3 previously unknown bugs. And we found we could type check these programs using about 80% fewer typecasts when we use CompTypes as compared to when we did not. So to get this to work, we're going to piggyback off this unique feature of RDL, whereby type checking is actually performed at runtime. So coming back to this foo example we saw earlier, type is actually a method that we're calling. In Ruby, the parentheses in the method call are optional. And we're passing the type method the string that represents the type of the foo method. And that string is going to be parsed into RDL's type system, and those types will be stored in a global table that maintains a program's type environment. And then when we call this RDL.doTypeCheck method at the bottom here, that's what actually triggers the call to type check our program. So that's when type checking will take place. So what this means for us is that types are actually runtime values that we can compute with. And that's going to be important because it means we can write type-level Ruby code that when we run it will give us other RDL types. And we're also going to make use of these things called table types. These are just basic generic types that we'll use to represent the return from joins call. So in these types, the parameter of the table type is a finite hash type that tells us the schema for a table. So for the joins example we saw before, where we join the user and email tables, we want that to return to us this table type at the bottom here, which reflects the schema of both the user and the email tables. And if we can get this return type from joins, then we can write a comp type for the exist method that looks like this. So in the input type, you'll notice these funny angle quotes, and what those are delimiters for some Ruby code. And inside this Ruby code, we have this identifier trec that's going to be bound to the type of the receiver of a call to exists. And we're calling trec.param0, which will just give us the parameter of the table type that is the receiver for this call. And we're going to actually run this code when we are performing type checking, when we encounter a call to the exist method. So for example, if the receiver of an exist call has this table type that we saw before, then we're going to bind trec to that table type. And then we're going to actually run that type level code, and we're going to determine that for this particular case, the input type for exists is this hash type, which tells us the columns we're allowed to query and the types that are associated with those columns. So the question now is, how do we actually get that table type? And for that, we can write another comp type for the joins method. So the comp type is shown here. The input type for joins is always a symbol that names the table we want to join to. And this notation means that we want to bind the name t to the actual argument type in a call for joins. So RDL uses singleton types for symbols, which means we can reflect the value of a symbol into its type. So in this particular example, t would be bound to the singleton type, which contains the value emails. And then the return type is again some type level code, which what it does is create a new generic type. The base of that generic type is tabled, so we're just making one of these table types. And by the way, the result of the computation for this particular case is shown at the bottom of the screen. And then the second line of this type here actually computes the parameter. So what this does is we're calling schema type of trec, the receiver type, and we're merging it to a hash that includes schema type of t, our argument type. So schema type is a method we haven't shown the code for here for the sake of brevity, but basically given a table name, it looks up that table schema in Rails and returns its schema as a hash type. So all this code is doing is computing a table type which merges the schema of the receiver and the argument tables. And that's going to give us the return type we want. So putting this all together, we were able to write a comp type for joins, which computes a table with a merged schema. We were able to write a comp type for exists, in which the input type depends on the receiver of the table it's called on. And so we're going to be able to precisely type check the larger query that we wanted to check. All right, now there's a whole lot more detail in the paper that we didn't have time to get to here. So we discuss how CompTypes lead to fewer manually inserted typecasts. And in particular, we found we needed fewer downcasts for operations over arrays and hashes. We discuss how we use dynamic checks to enforce the correctness of CompTypes. So one thing I didn't mention is that methods which themselves have CompTypes, we don't actually type check. We instead focus CompTypes on library methods which go unchecked. And this decision avoids issues of decidability, and it keeps our system practical for real Ruby programs. So instead, we use dynamic checks to enforce the correctness of CompTypes and to ultimately enforce the soundness of our type system. We also implemented a lightweight termination checker for type-level code, which ensures that type checking is terminating. We formalized our system, improved its sound. We implemented type checking for SQL strings, and we found a way to implement constant folding within our type checker using CompTypes as well. All right, so shown here are the libraries that we actually annotated. So we annotated a number of Ruby's core libraries: array, hash, string, integer, and float, and 2 database DSLs, ActiveRecord as we saw, and another one called SQL. So in total, we wrote 586 CompType signatures. And then this last column here shows the lines of code in helper methods. So what this means is in each CompType that we wrote, all the type level code would do is call out to what we call a helper method, which actually implements the type level logic. So in total, we wrote over 1,400 lines of code in these helper methods. So just a couple notable things to point out here. For a number of cases, we found that we could use very few lines of code to annotate a very large number of methods. So most notably in the integer and float libraries, we could annotate about 100 methods in each case using just the same 12 lines of type level code. And another thing to note is there's really a one-time effort involved here. So while there is a non-trivial effort, really just someone with some expertise can go through and annotate these libraries, and then you can use them to type check as many clients of these libraries as you'd like. So that's exactly what we did. We put these to the test against some Ruby programs, and the results of that are shown here. So this first column shows the benchmarks, the names of the benchmarks we type checked. All of these were chosen because they were well maintained, popular, and they all made extensive use of the aforementioned libraries, so we could actually test the type annotations we wrote. The next column shows the number of methods we type checked within each app. So these benchmarks were for the most part very large, and they still required a manual effort for things like annotating methods we wanted to check and annotating third-party libraries. So we selected a subset of each benchmark and focused again on those methods that would test our CompTypes. And in total, we type checked 132 methods. Next, we see the lines of code for the methods we type checked. So in total, we type checked over 1,300 lines of code. And then we see the number of manually inserted typecasts we had to write to type check these programs. So in total, we had to write 37 typecasts. But the subsequent column shows how many typecasts we had to write when we didn't use CompTypes. So we type checked all these programs a second time, and this time we found, this time without using CompTypes, and we found we needed 176, or about 5 times as many typecasts as compared to when we didn't use CompTypes. So this is really a testament to the precision that we gain from this CompType system. Then we see the median time over 11 runs of this type checker on these programs. So in total, we took just under 15 seconds to type check these programs. A large portion of this time resulted from kind of a quirk in Rails, whereby methods are lazily defined, and we actually discussed that more in the paper. And then finally, we see the number of errors we found in these programs, which I'll discuss now. So we found 3 errors across these benchmarks. One of these was actually a type documentation error in the code for code.org. So the documentation for a method said it would return one type. Our type checker found it returned a different type. And then the 2 other errors were type errors in the Journey app. So we confirmed all of these errors with the developers, and also in 2 out of 3 of the cases, we found that if we did not use CompTypes, we would get some false positives. We would get the wrong errors. And we would need to insert additional typecasts until we actually caught the true errors. By contrast, when we used CompTypes, we needed no additional typecasts. So again, we think the precision we gained from the system assisted us in catching these errors. So to just briefly conclude, we developed this system of CompTypes, which puts type-level code in method signatures and allows us to compute precise input and output types for Ruby library methods. We wrote CompType annotations for a number of key Ruby libraries, including database DSLs, and some of Ruby's core libraries. And we put these to the test against 6 popular Ruby apps and found we needed significantly fewer typecasts when we used CompTypes, and we also found 3 previously unknown errors in the process. So we think this is a promising step towards being able to more precisely type check programs written in dynamic languages. So that's all I have. Thanks to you all for listening.
So this is really cool work, and one thing that I think we could potentially learn from all the work you've done is whether there are some new abstractions that we can add to the type system that would cover a bunch of cases that you ended up having to write custom code for. TypeScript, for example, has been coming up with a whole passel of new, interesting type system, type constructors for joining and talking, combining and conditionalizing types. And I wonder if there's some other abstractions that you have seen here that could be integrated into RDL or into some other type system.
Mm-hmm. Yeah, that's a good question. So one thing we found throughout this process is there were some benefits of type-level computations that we could have gained if we added some kind of built-in support to RDL. But we ultimately decided that it was more beneficial to keep these just within method type signatures. So the reason being, so users can, for example, monkey patch methods in Ruby. And in that case, you don't want to go into the type checker and change the type checker itself. Instead, you could write a new type for those methods. And these libraries are constantly changing. So you wouldn't want to update the type checker for a bunch of different library methods every time it occurred. So we thought actually a benefit of this system was that we could sort of keep things as discrete types for methods, which would make it easier to go in for a user or for someone to change later on. So I don't know if that addresses your question, kind of, but.
Well, maybe we should talk about it later.
Sure.
Hi, Paul Yatar from Microsoft Research. So type signatures are useful both for type checking, but they also serve as documentation quite often. But here it seems like the type signatures become quite complicated and involve a lot of executable code. Mm-hmm. At least in the snippets that you showed. What's your thoughts on in practice, do your type signatures serve any documentation purpose?
That's a good question. Certainly, yeah, it does introduce more complex types. We still maintained non-computing types side by side with these, so I suppose those could still be used by the user. And as I mentioned, I think typically these types could be written by someone with some expertise, and then they can make for a more easy type checking experience for someone who actually uses them. In terms of documentation, I guess that's certainly something to think about in terms of how we could make these more readable and accessible to someone who's not familiar with a system like this.
Thanks.
Okay, next speaker, okay?